First thing we should do here is make a rough sketch of this. We're going to have a 35-degree angle and a 69-degree angle in there. So I'm going to draw a baseline and attempt to draw those two angles to the best of my ability. Let's do that over here. So here's a baseline. And then 45 degrees would be about there. So maybe 35 is down here-ish. From this side. And I might miss that. 45 degrees is about there. So 69 is going to be somewhere up here-ish. Probably. So there is my triangle. Let's extend that a little bit. It's going to look something like that there. So that's my best effort at drawing without a protractor, 35 degrees there. And that is what, angle A. And then 69 degrees is what I was trying to draw there. That's angle C. So angle B has to be up here. And then we have that whole opposite side thing. So down here, this would be B, the length, A, the side, and C. So let's make sure I got this right. A, 35, C, 69, and B is 17 there. And we want to use, excuse me, the law of sines to find, oh, B is 17, I should write that in there. Some of these other values. All right, so what do we got? Let's see. Angle B is listed first, so maybe we'll go for that. So we could say the sine of angle B, oh, I should get angle B. Since we know these two angles and they have to add up to one angle, we can get that right away. So let's do that first. So B is going to be equal to 180 minus 35 minus 69. Let's get that on a calculator. And we don't need that. So 180 minus 35 minus 69, 76 degrees. And then for some side lengths, and I think I'm gonna not start off with the sine there. So usually if I'm looking for the side length, I put the side length on top in the triangle, makes it slightly easier to solve. So for example, side A divided by the sine of angle A, 35, is going to equal, and now I need two things I know. So I know about B. Side B is 17 over the sine of its opposite angle, 76. Then we'll just multiply that sine up to get A. And then on my calculator, so I can, excuse me, not have to worry about rounding. I'm actually going to call it A. So 17 times the sine, 35, divided by the sine of 76. And again, make sure your calculator is in degree mode. And I selected degree mode earlier. So I get A is about 10. So 10.0493 maybe. To 2 decimal places, 10.05. And so that's this side over here. And I did try to draw this to scale. I did my best estimate without a protractor of 35 and 69. And if B is 17, yeah, I'll buy A should be about 10. That seems reasonable in my picture if my angles are drawn reasonably well. All right, side C, similar. C over the sine of angle C, which is 69. And then I'm going to use B because I know those exactly. I only know A approximately here. So I'm going to go back to side B as 17 and the sine of angle B, which we found to be 76. And similar, we multiply that sine up. And calculator time. And then for fun, we could test this with the law of cosines. So we think side C is equal to that 17 again, but this time times the sine of 69 divided by the sine of angle B at 76. So 16.36 to 2 decimal places. And let's think about the picture here. Does that seem a reasonable side length? Well, it's definitely bigger than side A. Should it be smaller than side B? Well, side B has the biggest angle, or sorry, angle B has the biggest angle, so side B should be the biggest side. Angle C is the intermediate angle here, so it should have the intermediate side length. And angle A is the smallest angle, so it should have the smallest side length. And my picture does have that. Those seem like reasonable numbers. Now, just for fun, I'm going to try the law of cosines on this. And it's going to be an approximation because of these values here. Although I do have this almost exactly on my Desmos. Desmos stores a ton more decimal places on that. So if I focused on, say, angle A and side A to check with the law of cosines for fun, right? Because how else are we going to check to see if this is right besides drawing it and see if it works? There are ways to do that, but that's something you might do in a high school geometry course. GeoGebra does that very well. I'll show a picture of that in the next video. So I'm going to go for this version of the law of cosines. A squared equals B squared plus C squared minus 2BC times the cosine of the angle between B and C, which should be angle A. And so I'm just going to enter these values into my calculator and see what happens. So my A squared, the square of this crazy thing here, so that's going to be about 10.5 or 10.05 squared, should equal approximately, because that's rounded, B 17 squared plus C about 16.36 squared minus 2 times 17 times 16.36 times the cosine of 35 degrees. Oops. So I'm just going to try that on my calculator, see what happens. All right, so I've entered A and C here, so I could just use those. So I'm focusing on A, so I'll write what's A squared, and I get it's about 100, right? So A was 10. And then the other side said to take the B squared. Well, B was 17, so I can just type 17 squared plus C squared, and I have C above, so I can just type C squared. And then law of cosines does a minus 2 times these two sides. So 2 times 17 times C, and then times the cosine of the angle between them. And that was angle A at 35 degrees. And I should get exactly the same number above using all of the accuracy Desmos had. Now, if I use like the 10.05 and the 16.36, it's going to be slightly different. So let's do that just to check. 10.05 is not exactly A, but it's close. And instead of C here, if I do 16.36, what I should see is the two numbers are close together, but they're not exact because I've introduced rounding error in 2 different places. Oh, 3 different places. 16.36. Right, so they're close to 2-3 decimal places out of 100. That's pretty good, not bad. So like a relative closeness, that's like they're within 1/100 of a percent, 1/10 of a percent of each other. That's reasonable with the approximations we did. All right, so we use the law of sines to find these here, and And yeah, pretty straightforward. Let's try another. A little bit of work though.